Today, we're tearing the lid off the AI black box, that sophisticated, complex system that, once in a while just seems to break bad.
It's such a critical topic right now. We're talking about these incredibly powerful models, deep neural networks, large language models that sometimes make decisions that are, well, they're biased, they're fragile, or sometimes just completely incomprehensible.
And it's not just that they get an answer wrong, right?
Yeah.
The real problem is we can't look inside and figure out why.
Exactly. We can't trace the logic. And what the sources we've looked at show is that this opacity, this secrecy, can lead to some really unsettling behavior.
Unsettling how?
The models sometimes learn to act secretively. They'll share half-truths or even purposely omit information because that's what gets them to the right answer fastest.
So it's reflecting the worst of the human data it was trained on. Obfuscation, shortcuts.
Precisely. It learns that an answer that looks good is better than one that's factually traceable. So our mission today is to really go beyond the buzzwords and dig into the technical and the regulatory efforts that are trying to force some transparency back into these systems.
Because the stakes are just, they're immense. When an AI is making a high-stakes call like a medical diagnosis or who gets a loan or even in criminal sentencing, a failure in transparency can have devastating real-world consequences for you.
We're talking about your savings, your freedom, your health. All on the line because the why behind a decision is buried somewhere in a billion parameters.
So before we can even demand accountability, we have to get the language right.
We do. There's a lot of confusion out there.
Let's start right there then. Before we try to open this black box, what is the actual difference between, say, explainability and interpretability? Because a lack of clear definitions, as some researchers pointed out, is what really kicked off this whole push for formal rules.
That distinction is, it's absolutely paramount. Let's start with interpretability. You can think of this as the how.
The how. So like the blueprint for the entire machine, the structural design.
Exactly. Interpretability is all about how easily a human can understand the model's overall logic, the entire architecture. It answers that big question, how does this thing actually function on the inside? An interpretable model is simple enough that you can basically trace the decision path before it even makes a decision.
Okay, that's the how. So then, if we're talking about one specific outcome, like my loan application being denied, that's where explainability comes in.
Yeah.
The why.
Yes, that's the why. Explainability is the ability to give you a clear reason for one specific decision after it's already happened. It's the set of tools and techniques we use to justify a single output from the machine. It answers your question. Why did the model say no to me?
And the big umbrella term that covers both of those, making sure all this information is actually available in the first place, that's transparency.
Transparency is the foundation. It's about access to information, how the system was built, what data it learned from, how it operates. You simply can't have accountability if you don't have transparency. It's the starting point for everything.
This makes the next point really clear. The difference between the tools people are actually using. So white box versus black box models. Let's start with the ideal. The white box.
Right, the white box model, or sometimes people call it a glass box model. These are designed from the ground up to be transparent. Their internal logic is easy to see because they're built on, pretty straightforward mathematical structures.
Like what? What are we talking about here?
Think of simple things like linear regression or a basic decision tree with clear if-then rules that you can just read like a flow chart.
But are these simple models actually competitive in the real world? Or are they just for, academic problems?
Oh, they're highly competitive in many, many domains. The sources we looked at highlight some pretty advanced versions like generalized additive models with pairwise interactions, or GA2Ms for short.
GA2Ms. What makes them so special?
Well, their architecture is inherently interpretable. A GA2M calculates a score by just adding up the contribution of each individual feature plus the contribution of specific pairs of features.
So instead of this tangled mess of connections, it's more like a clear, itemized receipt. You can see what each component contributed to the final price.
That's a great analogy. And what's really important here is that these GA2Ms achieved state-of-the-art accuracy in 2 different healthcare applications, all while being completely interpretable.
So that's huge. It's direct proof that you don't always have to sacrifice performance to get transparency.
Not at all, especially when you're dealing with structured data, spreadsheets with clear, meaningful columns. But
Mm.
the reality is that the models dominating the headlines in the high-stakes fields today are the black box models.
The deep neural networks, the LLMs.
Exactly. The ones where you put the data in, you get a result out. But the billions of parameters and the complex nonlinear layers in between make the internal logic completely opaque.
And because of that opacity, we get this dual problem. They hide their vulnerabilities and they hide their biases.
Correct. The complexity is so immense that even the engineers who built the system often can't trace a specific decision path. And that means if there's a subtle bias in the training data or some kind of fragility, it stays hidden until something goes wrong in the real world. That opacity is really why these systems sometimes seem to just turn evil or act in these erratic, untrustworthy ways.
Which brings us to what the sources call the high-stakes dichotomy. We're okay with a black box running a spam filter, but not a cancer diagnosis tool.
Right. I mean, if your chatbot gives you a weird answer, you just close the window. It's a low-stakes decision. The cost of failure is basically zero.
But when you're talking about fundamental rights or human safety medicine, hiring, the justice system, then transparency becomes completely non-negotiable.
It moves from being a nice-to-have feature to a core ethical and legal requirement. A doctor can't, in good conscience, tell a patient they have cancer based on an AI's say-so if they can't understand the reasoning behind it. If that decision is challenged in court, the hospital needs to be able to defend it. You can't do that if the process is a secret.
Okay, so this lets us challenge that big myth, the one you mentioned earlier, the performance versus interpretability trade-off myth. This idea that to get the best performance, you have to accept the black box. Is that really true?
It's a myth that has driven so much unnecessary complexity and risk. A lot of the time, developers just assume that a more complex model will be more accurate, so they jump straight to deep learning without even testing simpler, interpretable options.
So where does that assumption really fall apart?
It falls apart most clearly when you're dealing with structured data. Think about the kind of data used for credit scores, financial modeling, or recidivism risk. It's tabular, it has well-defined features. In those cases, simple interpretable classifiers often perform just as well as, or statistically similarly to, the big, complex black box models.
Why is that? Why can the simple models keep up?
Because for that kind of data, the extra complexity of a neural network often doesn't actually add more meaningful insight. A well-tuned linear model or a carefully constructed decision list can capture the important relationships without adding millions of opaque parameters.
People like Cynthia Rudin are arguing that we should flip the burden of proof.
Exactly. Instead of asking, why do we need an interpretable model, we should be asking, why do you need a black box if a transparent one gets the same result?
If a glass box model performs just as well, then deploying the black box is just adding unnecessary risk.
It's adding risk, it's adding regulatory exposure, and it's adding potential for real human harm. And while there might still be a performance gap in, say, high-dimensional computer vision, a lot of research is focused on closing that gap with new interpretable architectures. The message is, the trade-off is often more of an excuse than a necessity.
So if the black box isn't always necessary, then we absolutely need to know how to open the ones that are already out there. That brings us to Section 2. The toolkit for prying them open, the fields of explainable AI, or XAI.
Right. And the first thing the field had to do was get organized. There were so many methods popping up, we needed a taxonomy, a way to categorize them, and that taxonomy really breaks down along two main dimensions.
Let's start with the first one, approach type. Is the explanation built in from the start, or is it bolted on afterwards?
This is the divide between intrinsic or anti-hoc models and post-hoc methods. Intrinsic models are the ones designed for transparency from the ground up. Their architecture is the explanation.
Those are the white box models we talked about, like decision trees. Are there more sophisticated examples?
Oh, yes. Researchers are building specialized neural networks now. For example, there are concept bottleneck models, or CBMs, and proto-PNet. A CBM is fascinating. It forces the network to first identify a set of human understandable concepts before it makes a final prediction.
What kind of concepts?
So for a bird classification task, the concepts might be, has a yellow beak, has striped wings, is near water. The final decision can only be based on those concepts, which makes the logic traceable. The model is the explanation.
The upside there is that the explanation is guaranteed to be faithful. It's the real logic.
It's the real logic. That's the huge benefit. The downside is they can be harder to train. You might need humans to label those intermediate concepts, and sometimes there's a slight performance hit.
And that's in sharp contrast to what's most common in the industry today, which is the post-hoc approach.
Exactly. These are the add-ons, the interpretation techniques you apply after a complex black box model is already trained. Things like LIME, JAPE, GradCam. They're popular because you can apply them to almost any model without having to retrain it.
But there's a huge conceptual risk there, isn't there? If you're using what is essentially another complex method, the XAI tool, to explain your original black box.
The biggest danger is what we call unfaithfulness. The post hoc explanation is only an approximation of the real logic. It might generate a story that sounds perfectly plausible to a human, but it might not be the real reason for the decision.
It's a plausible lie.
It can be. And if the explanation is a lie, it completely undermines the entire goal of accountability. It gives you a reason, but not the true reason.
Okay, so that's the first dimension. The second dimension of the taxonomy is scope. Are we trying to understand the whole system or just one decision?
This separates local interpretability from global interpretability. Local is all about explaining one single prediction. Why was this image classified as a cat? A local explanation might be a heat map, a saliency mask showing you the pixels that lit up for the cat decision. LIME is a classic local method.
And global interpretability is trying to explain the model's behavior as a whole.
Yes, trying to extract some general knowledge. For example, can we generate a set of 10 simple rules that describe 90% of the model's decisions? Or can we plot how the model, on average, weighs the age feature across the entire dataset? You can sometimes get a global view by adding up thousands of local explanations, but that can also hide important details.
Since these post-hoc tools are what most people are using, let's dive deep into that toolkit, starting with the two biggest names, S-Shape and LIME.
Let's start with SAP, which stands for Shapley Additive Explanations. It's one of the most popular because it has this really strong foundation in cooperative game theory.
Game theory. How does that possibly apply to a machine learning model?
Well, think of it this way. In game theory, you want to fairly distribute a payout among a team of players who all work together. In SAP, the players are your input features, like age, income, credit history, and the payout is the final prediction.
Okay.
The Shapley value for a feature, say income, is its fair marginal contribution to that prediction, averaged across every possible combination, every coalition of the other features.
Wait, every possible combination. If you have, like, 50 features, that must be an astronomical number of calculations.
It is. It grows exponentially. That's the biggest drawback. The exact calculation is mathematically rigorous, but it's often completely intractable for real-world models.
So how is SAP actually used in practice?
They use approximations. For complex models, the most common one is called kernel SHE, which uses some clever sampling and a weighted linear model to estimate the true Shapley values. It makes it usable, but you're introducing another layer of approximation, another potential source of unfaithfulness.
Okay, so that's SHAP. Rigorous, but slow and often approximated. What about its main rival, LIME? It's known for being much faster.
LIME, or Local Interpretable Model Agnostic Explanations, takes a much simpler approach. To explain one specific decision, say for one loan application, LIME creates a tiny local map of the black box right around that single data point.
How does it make that map?
It takes your application, perturbs it slightly, changes the income by a little, the debt by a little, and gets a bunch of new predictions from the black box. Then it fits a very simple interpretable model, like a basic linear regression, just to that little cloud of new data points.
So it's like you have this giant, complex, curvy line, and LIME just draws a tiny straight line to approximate one little segment of it.
That's a perfect analogy, and the explanation is just the slope of that simple straight line. It's fast because it's only looking at that one tiny neighborhood. But this approach has two really well-known weaknesses.
Which?
First is fidelity. That little straight line might not be a very good approximation if the real decision boundary is really complex right there. The explanation isn't perfectly accurate. The second, which is a huge problem in high-stakes areas, is stability.
Stability. You mean you could get a different answer if you run it twice?
Exactly. Because the perturbations are random, the explanation LIME generates can change significantly from one run to the next. That inconsistency makes it really hard to trust. Is the variation because of the model's logic, or because the explanation tool itself is unstable?
So both S-shape and Lime have this core problem of being approximations. Let's talk about another approach, one that looks at the math of the neural network itself, gradient-related attribution.
Right. These methods actually use the structure of the model. In calculus, a gradient tells you the direction of steepest ascent. In AI, we can calculate the gradient of the final prediction with respect to the input features.
So it tells you if I change this input pixel just a tiny bit, how much does the final prediction for dog change?
Precisely. If the gradient is high for a certain pixel, that pixel is important. That's the basis for simple saliency maps. The problem is, for very deep networks, simple gradients can be misleading due to an issue called saturation, so more advanced methods were developed.
Like integrated gradients or deep lift?
Yes. There are just more robust ways of calculating that same core idea. Which parts of the input were most responsible for the output? They're much better at assigning the credit, or blame, to the right features for a specific decision.
All of this, pixels, gradients, weights, is still very technical. What about methods that try to speak a more human language? Let's talk about concept-based methods.
This is a huge leap forward because humans don't think in gradients, we think in concepts. We don't say a picture is a zebra because of pixel values. We say it's a zebra because it has stripes.
So how do you get an AI to think in terms of stripes?
A method called TCAV, which uses concept activation vectors, or CAVs, does this. First, a human user defines the concept of stripes by showing the model a bunch of example images with stripes and a bunch without.
Okay, so you teach it the concept.
You teach it the concept. Then, TCAV finds a direction, a vector, inside the network's high-dimensional brain that represents that concept. Finally, it measures how sensitive the zebra prediction is to that stripes vector.
So it's asking, if I nudge the model's internal representation a little more toward the stripes concept, does the zebra prediction get stronger?
Exactly. And you get a quantifiable score. This is incredibly powerful for uncovering bias. TCAV was famously used to show that a network was highly sensitive to the concept of gender, even when it wasn't explicitly trained on it. It found a strong link between the concept female and the prediction apron.
Wow, so it quantifies the stereotype the model learned from society. It's a perfect lead into our next section. But before we get there, two more quick formats. First, rule extraction.
Rule extraction is kind of the holy grail for compliance. It tries to distill the whole messy neural network down into a simple set of if-then rules. If income is over 50K and debt to income is below 30%, then approve loan.
Sounds great. Why isn't everyone doing it?
Because finding the smallest set of rules that accurately describes the network is what's called an NP-hard problem. The search space is astronomically huge. For a model with just 50 features, you're looking at more possible rules than there are atoms in the universe. It's just computationally impossible to do perfectly for large systems.
And the last format, counterfactual explanations. These seem the most user-friendly.
They're very intuitive. A counterfactual explains a decision by telling you the smallest change you could make to get a different outcome. Your loan was denied. If you had $1,000 more in savings, it would have been approved.
That's direct, actionable feedback. So what's the catch?
Two big ones. First, it tells you nothing about how the model works, only where the decision boundary is. But more importantly for the user, the smallest possible change is defined by a mathematical distance, not real-world cost or effort.
What do you mean?
The model might tell you that paying off a $500 debt is the smallest change, but for you, getting a different job that pays $50 more a week might be far easier to actually accomplish. The model has no idea about your personal context, your constraints. The explanation might be mathematically minimal, but practically useless.
This lack of context and the fragility of all these approximations leads us right to the real-world consequences. What happens when these opaque systems actually fail out in the wild?
That's when we see the bias get amplified, the hidden fragility get exposed, and sometimes even deliberate malice succeed.
When AI models are these opaque black boxes, they become incredibly powerful amplifiers for our own historical flaws. They soak up bias from the data they're trained on and then apply it at a massive scale.
Which is exactly why the simple idea of fairness through unawareness is such a catastrophic failure, is the idea that if you just remove sensitive columns like race or gender from your data set, the model will be fair.
But the model is smart enough to find clues elsewhere, right?
It's an expert at finding proxy features. These are other seemingly innocent data points like a person's zip code or where they went to school that are highly correlated with the sensitive feature you tried to remove. The AI just learns to use the proxy instead. It reverse engineers the bias.
And there is no more infamous or high-stakes example of this than the Compass recidivism risk tool, which was used in the U.S. justice system.
Right. This was a proprietary black box model used to help judges with sentencing and bail decisions. Its overall accuracy at predicting who would reoffend was, okay, about 61%. But that single number was hiding a massive, deeply disturbing racial disparity in the way it was wrong.
Let's really break down those error rates, because this is where the bias becomes so clear.
The analysis found that black defendants were almost twice as likely as white defendants to be incorrectly labeled as high risk. These are people the model flagged as dangerous who then went on to not reoffend.
A false positive.
Yeah.
An error that directly harms an individual, potentially costing them their freedom.
Precisely. This happened to 44.9% of black defendants labeled high risk, compared to just 23.5% of white defendants. On the other side of the coin, the opposite error happened.
The false negative.
Correct. White defendants were much more likely to be labeled low risk and then go on to commit more crimes. This happened 47.7% of the time for white defendants flagged as low risk, compared to just 28% for black defendants.
So the system was systematically making one kind of error for one group and the opposite kind of error for another. That's the definition of algorithmic bias.
It is. And the complexity of the model added another layer of unfairness, what the sources call procedural unfairness. The Compass tool required court clerks to manually enter data for over 130 different factors for each defendant.
130 factors. The chance for human error there must be huge.
It is. Even with a tiny 1% error rate per factor, the odds compound. On average, more than half of the defendant profiles would end up containing at least one typo.
So two people with the exact same history could get completely different risk scores just because of a random data entry mistake.
That's the procedural unfairness. The black box not only baked in historical bias, but also magnified the impact of random human error. And it's worth noting, the developer of Compass even testified he never designed it to be the sole factor in a sentencing decision. But once it's out there and it's opaque, that's how it gets used.
This opacity allows AI to be right for all the wrong reasons.
Yeah.
This brings us to the clever Hans effect.
Right, named after the horse that could supposedly do math, but was actually just reading cues from its trainer. The AI version is when a model gets high accuracy in training, but it's not learning what you think it is. It's learning a shortcut, a confounder.
And that medical example of this is it's a perfect illustration.
It really is. A model was built to diagnose COVID-19 from test x-rays. It achieved incredible accuracy on the training data, but when they deployed it in a new hospital, the performance completely collapsed.
So they used XAI to figure out what went wrong. What was the shortcut it learned?
It wasn't looking at the lungs at all. In the hospitals where the training data came from, very sick COVID patients were often too ill to be moved to the main radiology department. So they were x-rayed in their rooms using portable machines.
Oh, no.
The model learned that the word portable, which was literally annotated on the corner of the x-ray image itself, was a powerful predictor of COVID-19.
You're kidding me. It learned to read the word portable instead of learning to read a lung scan.
It took the path of least resistance. An interpretable model would have flagged this immediately. It would have said, hey, the most important feature is this text in the corner. But in a black box, this fatal flaw stayed hidden until it failed in the real world.
So we have inherited bias, we have hidden fragility, and then we have deliberate manipulation. Adversarial attack.
Right. This is where people actively try to fool the AI. Adversarial attacks exploit the fact that deep learning models, for all their power, are surprisingly sensitive. An attacker can craft a tiny, almost imperceptible change to an input that causes the model to make a completely wrong prediction. How can such a small change trick such a massive model?
It's a weird property of high-dimensional spaces, and the proof that this is a deep structural weakness is the existence of universal adversarial examples. These are single, specific patterns of noise that you can add to almost any image, and it will cause the model to misclassify it. So it's not a one-off trick, it's a systemic vulnerability.
It is. And attackers generate these examples using the model's own gradients against it. Techniques like the fast gradient sign attack use the gradient to find the quickest way to push an input over the decision boundary. It finds the smallest possible change that will cause the biggest possible confusion for the model.
And this isn't just a problem for images, is it?
Not at all. It exists in reinforcement learning, and crucially, it exists for text. An attacker can change a single character or swap a couple of words in a sentence, and a sentiment analysis model that was supposed to read a review as negative will suddenly classify it as positive, even though the sentence still looks perfectly fine to a human.
So whether the AI breaks bad because of bias, fragility, or malice, the root problem is always the same thing: opacity. If we can't see the logic, we can't trust it.
And that fundamental realization is what has pushed the entire global regulatory community to shift from just encouraging transparency to actively mandating it.
This global push for governance shows that regulators get it. You can't just solve the black box problem with more tech. You need rules. You need accountability frameworks. Let's start with what's happening in the U.S. with the NIST AI Risk Management Framework.
The NIST AI RMF, which came out in 2023, is a really important piece of voluntary guidance. It's a systematic framework to help organizations manage AI risk, built on 4 key functions that are meant to be a continuous cycle.
What are those 4 functions?
They are govern, map, measure, and manage. Govern is about putting the policies and culture in place for accountability. Map is about identifying where you're using AI and what could go wrong. Measure is about developing the tools to actually test for things like bias and fairness. And then manage is about actively mitigating the risks you found.
So it's trying to get organizations to stop treating AI risk as a one-time technical check and start treating it as a continuous business process.
That's it exactly. It forces a governance-level conversation and requires regular audits, moving responsibility from just the data science team to the entire organization.
Okay, so that's voluntary guidance. Let's turn to the big one, the legally binding one, the EU AI Act.
The EU AI Act is a landmark piece of legislation, really the first of its kind. It's built on a strict, risk-based framework. The more potential harm an AI system could cause, the stricter the rules are.
Let's walk through those risk tiers.
At the very top, you have unacceptable risk. These systems are just banned outright. Things like government-run social scoring systems or AI that uses subliminal manipulation. Then you have the main category, high risk.
And what falls into that high-risk category?
This is where you find AI used in critical areas: medical devices, hiring, employee management, pay decisions, law enforcement, the justice system. For these applications, the obligations are incredibly stringent.
So for an AI that helps decide who gets a promotion, what does the Act actually demand?
It demands that the system cannot be an opaque black box. You need extensive technical documentation detailing how it was built and tested for bias. You need robust data governance to ensure your training data is high quality. You need logging capabilities so that every decision can be traced back. And crucially, you need meaningful human oversight.
That documentation requirement sounds like a direct assault on the whole proprietary algorithm business model.
It absolutely is. It forces a level of transparency that many companies are not used to. The Act also requires that any AI-generated content, like deepfakes or text, must be clearly labeled as such, which is a direct counter to deceptive AI.
And we're even seeing this kind of thinking at the state level in the U.S. now.
Yes, California's SB 53 is a great example. It's targeting the developers of the largest, most powerful frontier AI models and holding them accountable. This has immediate strategic impacts for any business that uses these models. Well, for one, it means you have to go back and check your contracts with your AI vendors. Do you have the right to audit their systems? It also introduces things like whistleblower protections for employees who flag AI risks. It puts the burden of accountability squarely on the organization that chooses to deploy the AI.
So all of this regulation is transforming professions like internal audit.
Completely. The job of an auditor is shifting from just checking compliance boxes to being a strategic advisor on AI risk. They need to understand SAP, LIME, and adversarial attacks now because they have to be able to audit the AI's logic itself.
And there's a perfect example of this pressure in the EU with the AI Act intersecting with the Pay Transparency Directive.
This is a fascinating collision of regulations. The Pay Transparency Directive says employers have to be able to justify their pay decisions to root out gender pay gaps. The AI Act says any AI tool you use for those pay decisions has to be explainable.
So HR departments can't use a black box AI to run pay remediation simulations if they can't explain to an employee or a regulator exactly why the AI recommended a certain raise.
That's the strategic consequence. It's forcing organizations to abandon opaque systems for their most sensitive HR functions. Regulation is mandating transparency right where it matters most.
So we have the technical tools to open the box and the regulations to force the box open. But there's also a third category, technical safeguards, to prevent certain failures from happening in the first place. This is where differential privacy comes in.
Differential privacy, or DP, is really the gold standard for mathematically proving and protecting privacy in data. It provides a very strong formal guarantee.
And what exactly is that guarantee?
DP guarantees that the output of your algorithm, your trained AI model, will be almost exactly the same whether or not my specific data was included in the training set.
So it hides individuals in the crowd.
It does more than hide them. It makes their individual contributions statistically insignificant, which means the model can't leak specific information about them. This is absolutely critical when you're training models on sensitive health or financial data.
How do you actually implement that when you're training a huge neural network?
The main technique is called differentially private stochastic gradient descent, or DPSGD. It's complicated, but it involves two key steps during training. First, you do per example gradient clipping. This limits how much influence any single person's data can have on the model's learning step.
So it caps the impact of any one outlier.
Right. And second, after clipping, you add carefully calibrated noise to the aggregated gradients before you update the model. The clipping limits the signal from any one person, and the noise then drowns out what little signal is left.
And there are toolkits like JX Privacy that help people do this correctly.
Yes, because it is very difficult to get right. And these toolkits also allow you to audit your privacy guarantees. You can do things like inject a canary, a fake known data point, into your training data.
And then you see if you can find it later.
Exactly. If your DP setup is working, the canary's presence should be completely undetectable in the final model. It's a way of empirically testing that your privacy promises are actually holding up.
It's so clear that the technical solutions and the regulatory mandates are finally starting to move in lockstep. Both are recognizing that opacity is the real enemy here.
When you put everything we've talked about together, the technical flaws in our explanation tools, the real-world harm of a tool like Compass, the sweeping mandates of the EU AI Act, the conclusion is pretty stark. The real danger of AI breaking bad isn't some kind of conscious malice.
It's opacity. It's the combination of technical secrecy and high-stakes deployment.
Exactly. You can't manage what you can't measure, and you absolutely cannot control what you don't understand.
And this is leading to some really provocative policy recommendations that could completely change the AI industry.
It is. The sources we reviewed put forward a really powerful mandate. For certain high-stakes decisions, no black box should be deployed when an interpretable model with the same level of performance exists.
Wow. That would fundamentally change the business model for so many companies. If you're selling a proprietary black box for credit scoring, your whole value is in that secret sauce. But this would force you to prove that your secret sauce is actually better than a transparent, simple model.
And very often it's not. It would force innovation toward making interpretable models better, rather than making black boxes more complex. It would effectively ban risky, opaque AI from areas like the justice system, unless there was a compelling, statistically proven reason for it to be there.
Ultimately, what we've seen today is that AI's tendency to be biased or fragile or secretive is just a reflection. It's learning from us.
The only way to build reliable, non-discriminatory AI is to design systems where the decision path isn't just documented for a regulator, but is fundamentally understandable to the people who have to use and trust it. We need to know the reasons it gets things right, so we can quickly fix the reasons it breaks bad.
Which leaves us with the final thought for you to take away. We talked about how AI can learn a shortcut, like the word portable on an X-ray, because it lacks the deep domain knowledge a human expert has. So here's the question. If AI were forced to explain itself to you in your field of expertise, if it had to justify every single decision using concepts you understand, what is the specific knowledge that you have that the AI would need to learn to become truly trustworthy?
Because the future of trustworthy AI probably depends less on how complex we can make the models and more on how clearly they can explain themselves to us.
Thank you for joining us on this deep dive. We'll see you next time.